There's A. I have the reaction force at A. That's we just decided RAY. That's 166.6 pounds of force. That's a positive, and we have some kind of force this way, some kind of forces this way. There is only one. This is in the y direction, positive, and this is the only thing that possibly could counteract it. So it must be like that. Must be going down to counteract the force, the reaction force at A. And you know there is no force in the x direction to counteract this one. So this must be 0. That one goes away. This is a 0 pounds. 0 pounds of force. 0 pounds of force, man. So that's nothing. That's 0. So that goes away. That's pretty sweet. That member is, you know, only there to counteract maybe expanding or contracting if it's cold or hot or something. So yeah, that doesn't make a difference there. So then what do we? Oh, well then that means right away I know this force. That force has to be opposite that force. So this is 166.6. Repeating. What is that one? That one is AD. AD 166.6 pounds of force. And we have to decide, well, if this points down, this points up to keep the member from moving, that means it's in compression. It's a compression, so I put it here. It's a compression. C stands for compression. Also stands for cookie. Alright, what the heck am I saying? What joint next? We're done with joint A. That's the easy one. That's the easy joint. Let's just see. I think I want to do joint D. Let's take a look at joint D. So this is joint A. Joint D, I write it down. I spell it the same. Joint D. And I write it down. This is joint A. This is joint D. The knee bone's connected to the thigh bone. What? I have C going upwards. No, not C. AD going upwards. That's 166.6 pounds of force. I know that because it's the force within the member. So, and I just found that. FAD. And then I have a force maybe going. This is too small. Alright, this is too small. 166.6. Repeating. That works. I have a force going like that, and this one I know, this one is horizontal, and it is 100 pounds. I have that 100 pounds. It's very good. I'm very popular with it. That's very good. And this is also pounds. We don't forget the units. And then, there's only other. This is in the y direction, and the only other y direction I might have, this is x direction, this is x direction. So the only other y component is the y component for that. And it must be pointing down. It must be. Right? So it can counteract this. So that mean that this one is pointing down like that. So I draw that. Just put the B back. And I draw this in there. Has to be like that. Has to be. So I take a look at this and I say, this has to be like that, this has to be like that, and that means this is under tension. You understand? No? Well, keep watching. So now I know, what is this? That is the force within dB, right? BD. I think I labeled it BD. BD, and I also know that the force of BD in the y direction, that must equal 166.6 repeating. Has to. Because it has to counteract that. That's the only other y direction force. So, since we have that, I can use SOHCAHTOA. Remember, you can only use SOHCAHTOA when you are, you have a component force and you're solving for the regular force, or you have a regular force and you're solving for the component force. That's the only time you use SOHCAHTOA for forces. So that's what we're going to do. To do that, though, I need an angle. So I'm going to draw FBD all by itself, and then I'll draw its component which is FBDY, that's 166.6. And what do I want to find? I want to find FBD, I think. FBD, that's ugly. That's very ugly. So I'd say if this is small, BD, this is still not very pretty. And I have a right triangle. Now, here's the thing that gets confusing for students, because the angles within the forces are the same angles within the members, right? That angle is the same as that angle. Well, I could figure that angle out with the SOHCAHTOA or maybe Pythagorean theorem. No, not Pythagorean theorem. So I can use SOHCAHTOA to find that angle, because the angle between the members is the same as the angle between the forces. So I draw a triangle. I draw the triangle. And this time is with members. This is with distances. So I can figure out the angle. And that will be is 5 on the bottom and a 6 on the top. Right? It's a 6 on the top. So there's a 6 there, there's a 5 there, and I use a tangent. I'm going to call this one theta 1. So as I say, is tangent, which is opposite over adjacent, tangent of theta 1, that be equals to 5 over the 6, which means I can do inverse tangent of the 5 over the 6, and that will give me theta 1 equals to 39.806 degrees. I have that now. And now I put the angle into here. That's 39.806 degrees. So now I can get FBD. Now I use SOHCAHTOA because I have the component, and the actual force is what I want to find. So that's adjacent over the hypotenuse. So I use SOHCAHTOA with the distances to find the angle, because that angle is the same as the angle between the forces. And so now I'm only using forces, right? So now I can use SOHCAHTOA again. I cannot use like SOHCAHTOA between two separate forces, like F, AD, and F, BD, just because, well, I mean, in this case, they're the same, FAD and the Y component. They just happen to be the same, but you can't always do that. So you just make sure you're using SOHCAHTOA between forces and their components. So, this is, this is cosine, we said this already. Cosine is the 39.806. That must equal to 166.6 repeated over the force of the BD. Yeah, and I switch those two. I switch them. I have them. I switch them. I switch them like this. I put this like this, over like this, and like this. And it's a cosine 39.806. I put it in a calculator. I put it in there, and I get the answer. It's very simple. And I get a 216.951. It says pounds of force, and I know that this one is tension, and that's between BD. No, 216 point. It's in red. I did not mean to do that. 51 pounds of force is tension. We say yes. We say it's tension. It's tension. It's tension. So that's very nice. We have that. That's very good. That's very good. Oh, you know this. You see this? You see this has x component that way. This has x component that way. And this has x component in one of the ways. I do not know this. I do not know which way it is. But look, remember. So we have that. That's very nice. For joint D, the sum of the forces in the x direction, the sum of the forces in the x direction, this must equal to 0. So I have 100 pounds in the negative direction, 100 pounds. And I have, what is FBDX? FBDX, this is the positive direction, FBDX. Those counter each other, but I do not know which one is stronger. I need to find FBDX. Well, how can I find FBDX? I can use SOHCAHTOA, right? FBDX is this one, right? This is the X component, this is the Y component. So I can't find that. I have this angle already. So FBDX. Well, I want to find that. That's FBDX. So this will be opposite over the hypotenuse. And I have FBD. So that we can say opposite over hypotenuse. That is sine. Sine of the angle 39.806. That's going to equals to the sine would be opposite FBDX, BDX over the FBD, which we say is 216.951. I'm done with that, boys. Been going for 20 minutes, man. Yeah. So I'll multiply both sides by 216.951, and FBDX equals 138.890 pounds. So in the X direction, this is 138.890 pounds. So the right side is winning out. So that means this plus this has a net force of 38, right? Because this is 38 more than that. 38.89 in the right-hand direction. So to counteract it, so this is winning by 38. To counteract it, that must be 38.89. Yeah? Okay. So let me write that down. We just discovered this has to be that way. Well, that means this has to be that way. This is under compression then. Yeah. And we know it must be the excess. It must be the excess. Look at this. You rewind it a couple seconds. Watch it again. These have to add up to counter each other, but they're not equal. So there's 38 left over, and it's in the positive direction. So to counteract it, I must have 38 in the negative direction. So that means DE, that should be 38.890 pounds. And we say this was a compression. We said it's compression. It's